This is lab 3 black hole. So the purpose of this experiment is to predict the mass of the black hole by analyzing the orbit of a star and to find the initial velocity of a spaceship using the determined mass to get close enough to the black hole without crashing into the planet or the black hole. So the results was that the mass of the black hole was determined to be 9.45 times 10 to the 33 kilogram, and the initial velocity of the spaceship was negative 5.2 times 10 to the 7 in the x direction, 1.89 times 10 to the 6 in the y direction, and 0 in the z direction. So one of the fundamental physics principles used is the law of gravitation, which basically states that the Fg is equal to g times m over the magnitude of r squared times a negative r hat. And Newton's second law, which basically states that F net is equal to the change in momentum over the change in time, and F net is also equal to F net parallel plus F net perpendicular. And F net parallel changes the magnitude of the momentum, and it is either parallel or anti-parallel to the direction of motion, while F net perpendicular changes the direction and is perpendicular to the direction of the motion pointing towards the center of the circle. So the velocity and position update formulas are also necessary, and it is stated below, and also the assumption that when F net is equal to the law of gravitation, the mass, big M, is equal to F net times the magnitude of r squared divided by the mass of the star. That's basically rewriting the law of gravitation equation. So these are the initial conditions. So for part 1, the initial time was 0 seconds, and the delta t was 864,000 seconds, which is 1 Earth day, and the mass of the star was 2 times 10 to the 30th kilograms, and the gravitational constant is 6.7 times 10 to the negative 11. So for part 2, the initial conditions are shown here, and we have the mass of the black hole along with the gravitational constant, the mass of the planet and the ship, and also the planet speed and planet velocity, which are set here. And so for part 1, the system is the black hole and the surroundings is the star. And for part 2, the system is the spaceship and the surrounding is the planet, the black hole, and just everything else. So this is part of the code for part 1, finding the mass. So we changed the initial momentum and the final momentum, and then we calculated the delta v and delta p by doing final minus initial, and then so dp over dt, the change in momentum, is delta p over delta t, and so using Newton's second law, F net is equal to dp dt, and then we calculated F net parallel. We found p hat, which is the direction of F net, and then we found the change in momentum in the parallel direction, and we multiplied that by p hat, and so we have F net parallel, and then we also calculated F net perpendicular, since F net is equal to F net parallel plus F net perpendicular. F net perpendicular is equal to the change in momentum minus the change in momentum in the parallel direction. And so because of that, we can find the mass of the black hole using the formula that was in a few slides ago, and that's shown there. And this is the result for part 1. So the mass of the black hole was 9.45 times 10 to the 33 kilograms. And then there were also the magnitude of F net and F net parallel and F net perpendicular are also shown. And so one of the possible errors is that the mass of the black hole was approximated, so there could be human error for those approximations. And this is part 2, calculating initial velocity of the spaceship. So we first found R hat, R, and then we found R hat. And with those two, we could find the force of gravity, for this one is force of the black hole on the planet, and then we found the force of the ship on the planet, and then we found the total force on the planet by adding those two together, and then we repeated the same steps to find the total force on the ship. And then for the planet position and velocity and the ship velocity and position, we did the velocity update formula and the position update formula. So the result was that this was the initial velocity, and some of the possible errors was that the initial velocity was determined through trial and error, which means that there could be slight human error, and that there's also could be other forces acting on the spaceship that we don't know of. So what does it mean? So parallel and perpendicular components of the net force and the parallel and perpendicular components of the rate of change of momentum are the same mathematically, but they require different components to solve. The net force requires the mass of the black hole, while the rate of change of momentum uses velocity and mass to solve as a function of time. So instead of wanting to take a quick look at the black hole area and leave, we want to enter in an orbit around the black hole, and what initial velocity would it be? So using trial and error, I found that if you use an initial velocity of -5 times 10 to the 6 in the x direction, 1.6 times 10 to the 7 in the y direction, and 0 in the z direction, the spaceship was able to enter in an orbit around the black hole without crashing into the planet.